Thank you. I'm excited to talk about this because in years past, there's been like parts that I've glossed over and I got to like put in a little bit more detail, but I'll have some like repetition, but most of it will be, not most of it, but 50% is kind of newer stuff to try and emphasize kind of key points. I probably brought way too many slides, so if I end up skipping some, just please forgive me, and if I talk fast. My main goal is to kind of talk about kind of leveraging social networks for sampling. I think that we have a kind of traditional sampling frame in the kind of way we do research, where we think about like we're going to collect data on people that we randomly pick to be in the study. But I think often that precludes, as Jim was saying earlier, precludes the ability to sort of study connections between people. And so there's been this long intuitive idea of like using the connections between people to get people into samples, to learn a little bit more about their social worlds and things like that. And I think the kind of methods I'm going to talk about kind of speak to that. I'm also going to give a lot of intuition about how these methods work, and then talk in specific about respondent-driven sampling, and then pivot to kind of other approaches, including network sampling with memory, which is probably the other biggest approach that has a kind of inferential framework tied to it. So just to give a basic reminder of how this stuff works, the idea of inference is that you can draw a small sample from a pretty large population, and you can make estimates about the characteristics of the population with reasonable accuracy. You know, the law of large numbers and other things like that prove to us that as we increase sample size, the kind of margin of error on our estimates tends to decline, and if it's a simple random sample, it tends to be unbiased, and that kind of marginal return of additional cases isn't actually super high once you reach a certain point. It's a nice feature. It allows a lot of the social world to exist. It allows us to do a lot of really exciting kind of social science. However, social science is in what I think of as like an existential crisis regarding the way we do sampling, because samples have been increasingly difficult to collect. This is a set of major surveys that have been fielded over time from the mid-90s. This ends in 2015, but extend this a few years, another decade forward, and you can see that response rates in surveys are declining really precipitously. So whereas we used to go out and field a sample and 90 out of 100 people would respond to it, now we're getting down into the 75%, and even in like recent major surveys that they spend a lot of money on, 55, 60%. Polls like random digit dialing telephone surveys have sort of a similar problem as shown there. And the problem is kind of even more compounded because while we have these 75% response rates in things like health and retirement survey and panel study of income dynamics and general social survey, that it comes at the cost of huge increases in how much they're spending to get people into the survey. So survey costs per case have gone up really dramatically. This is an estimate from the panel study of income dynamics 2017 wave, where they estimated that on average they were spending $270 per person they got into the survey in that wave. And that, of course, is higher when people actually enroll in the survey, and those non-responders are substantially more expensive. So you can imagine that this is driving up survey costs all around, which, of course, we don't live in a world of like infinite kind of survey and social science resources. In fact, we live in a world with a very, very existential crisis piled atop the existing one around how we are going to fund surveys. These are the proposed budgets for fiscal year 2026 versus 2024. You can see in the major scientific organizations that collect survey data, like NIH, NSF, the proposals are just extraordinarily dire, 30 to 40% cuts across some of them. And so I think that we really need to develop new ways and really revitalize the tradition of collecting survey data. I think that the large kind of like infrastructure surveys like panel study of income dynamics or others are actually under a lot of risk because these are big projects that they can cut and then save $50 to $100 million by cutting it, which would be dire for the field. But in addition, we really need to be able to field high quality surveys with substantially fewer resources. And if you're interested in specific populations, I think that it's a really important area to kind of think about how can we collect data in a way that is cheaper and more effective than the traditional ways. There's a lot of different ways to move forward in that kind of crisis. One is this idea that we can use administrative data. We could use medical records, for instance, and create cohorts from medical records data and follow them as they transition over time into different health states and things like that. I think there's ethnographic and qualitative approaches that deserve additional attention in this kind of dire environment to continue to do high quality social science research. Another area that has received a lot of attention is kind of online or digital trace data, how we can collect data from people's interactions on, say, Facebook or something like that, and learn about the world. And then the last that has kind of persisted in a lot of fields is this idea of convenience sampling. With all of these, with the possible exception of ethnographic qualitative data, the real challenge here is there's really uncertain generalizability. You cannot necessarily make that inference from the people that you have in your sample to the population as a whole. And secondarily, there's big reproducibility and sharing issues with a lot of these. You know, it's very difficult sometimes to access medical records data. It's not something that you could easily send to a colleague or something like that. There's all sort of privacy rules. And there's kind of limited measurement validity in a lot of these studies, with the exception of the qualitative stuff. You can't, for instance, say, are people lonely? You have to use a diagnostic code for depression in medical records data. So you can't look at all the things that you might be particularly interested in, which I think leads us into can we think of other options? So the other option that I think has the most promise is this idea of sampling from social networks. The idea here is we start with one person, they refer us to another, and we can begin to enroll lots of people in our sample, and from that sort of data, we can learn about the population as a whole. I want to take a kind of little step back and just mention this idea of hidden populations. I think that hidden populations are, they have a kind of classic formal definition as populations that lack a sampling frame, or are otherwise unwilling to participate in a survey because they're very rare, they're stigmatized, so they're unwilling to kind of feel trust with the researchers, and they have high rates of non-response. I think that what network sampling methods were initially designed for were these hidden populations, but almost all populations have become, or are becoming hidden populations. So I think we could think a little bit more broadly about that. A lot of hidden populations are classically of interest for kind of population health scholars, including people who inject drugs, people who are homeless or unhoused, sexual gender minorities, and kind of other groups that are of interest for social scientists and health scholars. The hidden population literature very much mirrors what can we do in the existential crisis kind of world, but we can't do things like digital trace data. It's very difficult to use administrative records for them. And so people have really, when trying to understand, for instance, people who inject drugs, they've relied heavily on convenience samples, or they've relied heavily on clinic-based samples, taking, for instance, the people who show up to a rehab clinic. Of course, the people who show up to a rehab clinic might differ in very important ways from the broader population of people who inject drugs, and so you might, by just studying those who are in the clinic, come up with an imprecise or inaccurate definition of or estimate of what proportion of them need Hep C care or something like that. So the problem with all of these kind of classic methods is, are we learning about people other than those who are in the sample, right? It's one thing if you have 200 billion or 200 million users of a web app, for instance, and you can only generalize to that 200 million people. That's maybe very significant. But if you're in the kind of traditional survey world where you're sampling maybe 1,000 or 500 people, being only able to generalize to that 500 people might be a very significant limitation for your kind of analyses. This is where the kind of classic method called respondent-driven sampling comes in. Respondent-driven sampling was originally kind of conceived by sociologists, sort of taking the insights of a snowball sampling approach where you have people and they refer their friends and others into the survey, but putting some major constraints on it. The idea of constraints is that instead of letting just people willy-nilly refer others, you give them kind of instructions like, please refer people at random. People can only refer a few people rather than one person referring 5. It's typically one person is allowed to refer 2, maybe 3, so that you get kind of more spread. And I'll explain why that's important in a little bit. RDS is super popular, as Jim had mentioned. In my estimates, I counted about 120 NIH-funded studies that have used RDS, and a very, very much larger proportion, or much larger number of studies that have been funded by WHO and other Gates Foundation and other major funders. There's lots of papers written about RDS. It's a very vibrant kind of research field. I think it's one thing that I like to do is benchmark it against kind of classic social network methods. RDS is, by many different ways of thinking about it, 5 to 20 times larger in terms of the amount of public health resources that have been put towards collecting that kind of data versus, for instance, egocentric network data. So RDS is typically used for hidden populations. Probably the biggest use of it is for people who are using drugs. but there are also a lot of uses for other kind of key populations in the kind of STI space, as well as other groups that have kind of piqued researchers' interests, like jazz musicians or vegetarians and vegans, as well as groups that face real stigma and real challenges, like domestic violence survivors, victims of sexual violence, and other people. The big funders for RDS historically, under the current system, who knows, but historically big funders for this had been kind of institutes within SN&H that focused a lot on infectious diseases or drug abuse. So NIDA, NIA, NIMH, mental health. And the typical kind of idea behind RDS is trying to learn quantitative things about the population of interest. I would say like the modal question for RDS studies is like, what proportion of people have HIV in this population of interest? If we're interested in people who inject drugs, what proportion of them have some STI of interest or bloodborne infection of interest? If we're interested in people who are jazz musicians, there might be a question of like, what proportion of them are living on the streets, that sort of question. We also try and characterize the population, and then there's a whole RDS literature about using this data to estimate the size of that group. So you might be interested in how many people who inject drugs are there in Boston versus Hartford, and RDS methods have been proposed to sort of estimate the size of those different groups so that service kind of efforts, maybe like there's a New England task force for people who inject drugs, and maybe they would have a larger service effort in Boston than Hartford because the population there is larger of people who inject drugs. RDS is used in a lot of fields, primarily in the public health world, but also in social sciences. And I'm going to skip over this quickly, but there are a lot of major resources for RDS kind of analysis. There's really good manuals to kind of design RDS studies, like the World Health Organization has a nice manual, CDC has a nice manual. And there's a lot of software out there for RDS kind of analysis, including an R package that makes it very easy to estimate the features that you're interested in and apply multiple different estimators. So to give a kind of base overview of RDS, I think of it as having two key components. The first is this chain referral idea, where you get like seed participants who are typically a convenient sample, maybe people that attend a clinic or something like that that are in the population, and often it's recommended that they have kind of high popularity. You say, hi, we're doing this study and we would like you to recruit others. You give them coupons to recruit others, and I might receive a coupon and then I would give it to people I know, like Lynn and Jim. And they would have that coupon and they would be eligible to participate in the study. If the only coupons that were distributed were those two, nobody else would be at that point. But once they come in and participate in the study, they get coupons and then they can do the same thing, and that kind of coupon process multiplies. And by tracking kind of the identity codes on the coupons, we can see sort of who recruited whom, and we can sort of follow the chain over time. The process is typically continued until the desired sample size is obtained. There's an implicit kind of assumption that is often enforced in practice but not always talked about, that nobody participates more than once. A challenge of enforcing that can be, in certain populations, that can be difficult. If people, if you have multiple research assistants or multiple sites, that can be difficult to kind of police. And the key idea here is that the researchers are not controlling the sampling process. It's respondent-driven, right? So the people that are in the population are those that are doing your recruitment. The second part of RDS is the entire statistical apparatus around RDS, which is weighting the cases to account for the kind of biases that would arise from that referral-based sampling process to try and generalize to the population of interest. So you're basically correcting for the theoretical sampling process, and then you make inferences about population averages or uncertainty in those averages that you've estimated. As I mentioned, typically RDS starts with a group of seeds. Usually you'd start with the recommendation in classic literature is 7 to 10. And you usually try and target people that are in the population, have large personal networks, and are a little bit diverse on different attributes. So you might look at people who are in a clinic as well as people who are not in a clinic. Or you might look at people who've used drugs for a while versus newer entrants, and you try and diversify that initial seed population. You then give them a couple coupons each and ask them to recruit others in the process I described. That allows you to sort of track who participates. Typically, people use physical coupons for this process. It's a little bit easier to control rather than web links or things like that. But there have been newer efforts to sort of diversify that and come up with kind of newer ways of tracking people's referrals. The web links really complicate, for instance, only allowing one person to participate per referral code, right? So there's some challenges with that. The resulting data from RDS typically looks like this, with the seeds kind of arranged at the top. This is from a paper by Giovanna and Jim, with the seeds arranged at the top, and each wave sort of stacked here. So you start with a small number of people, and most people recruit others, but although that person in the top left did not recruit anybody, and then the seeds sort of multiply and multiply and multiply, and you get a larger and larger number of people. Here, the nodes, I believe, are colored by the kind of popularity or the degree of the or sized by the popularity and degree of the respondent, and colored by what tier of sex work they are in. What you kind of see intuitively from this is that people, because of homophily in the underlying network, are tending to recruit people that are in the sort of same social world as themselves. Hence why the cyans are recruiting cyans, and the, I don't know what color I would call that, coral are recruiting coral, etc. I think it's also helpful to remember with RDS that there's both typically a primary interview where people enroll in the study for the first time, and then the opportunity for a secondary interview after they recruit others and their coupons have been redeemed. They can usually come in, and it's typical that you pay people an extra $5 for each person, each coupon that was successfully redeemed. So when they recruit one person, they get $5. If they recruit two people, they get $10, which gives an opportunity for a secondary kind of interview. And there's some interesting dynamics with that you can leverage to come up with cool network estimators, and I have some papers that have tried to look at that. So I want to give intuition about RDS because this is something that I feel like I have glossed over in the past. So the intuition behind RDS really comes from the random walk literature. The basic idea is that your probability of giving a coupon, assuming that you're giving coupons randomly, your probability is going to be conditional on the number of people you have. So if we take this underlying network right here, and we can represent sort of the one-step probability of giving a coupon. So if we look at node number 8 right there, node number 8 is connected to 3 other people, right? And so they have a 1/3 probability of giving it to node 3, 7, and 9. Right? Each of them have a 1/3 probability. Versus if we look at node 3, they're connected to 2 people, so they have a probability of 50% of giving it to node 7 and 50% of giving it to node 8, right? That's sort of the one-step probability of RDS. We can also kind of use that to say, what's the probability that you would get a coupon in this undirected network? So if we started, if we're interested in kind of the probability of reaching node 3, and we were to start with node 7 versus node 8, we would see that node 7, you have a smaller probability if you have only one coupon of passing it to 3 if you pick randomly among all of node 7's friends than you do among if node 8 is the one with the starting coupon. Because node 8 only has 3 friends, so they have a 1/3 probability of giving to 3, whereas 7 has, I think, 5 friends, so they have a 1/5 probability of giving to 3. And so where you start and where it ends up, those probabilities are different based on the network. The beautiful thing about responder-driven sampling or random walk processes or Markovian processes on graphs in general is that doesn't matter in the long run, right? All that matters is not where you started, but where you're likely to end up. And that's what the rest of this figure here is going to show. So this is the one-step probability. This is the 2-step probability. So if you start, say, with node 8, your probability of ending in 2 steps at node 3 is conditional on how many ways you can get to node 3 in 2 steps. So 1, right? That's the only way you can get to node 3 in 2 steps from node 8. And you can then calculate the 3-step and the 4-step, et cetera. And what's really cool about this is that as we get to, say, I think this is like 9 steps, we start with this kind of blocky or like sparse kind of network. But as we get down here, we see that the probability of ending up at a specific node is almost not conditional at all on where you started. So if we look at, by this step, your probability of ending up at node 3 is pretty low, and it doesn't differ a lot depending on which person the coupon started with. That's like the key insight behind RDS. Whereas your probability of ending up at node 3 is pretty small. Your probability of ending up at node, say, 6 is pretty high, right? And again, that same like convergence of the probabilities based on the attributes of the in degree of the receiver rather than where you started is the whole key insight behind RDS. To put that in numbers here, this is just simple matrix algebra. I started with a really simple connected network. This is, in node 2 is connected to node 2, 3, 4, and 5 in this kind of undirected network. In one step, these are the probabilities if you multiply. First, you have to compute like a Markov matrix. So you're going to take this over the sum of the rows. So if you are connected to 3 people, each person you could pass to is 1 over 3. If you're connected to 4, each person you could pass to is 1 over 4. Once you create a matrix M that's like a Markov transition matrix, if you multiply it 1 time, you see like, okay, these are still pretty different. Multiply it 2 times, they're still pretty different. 3 times, your probability of ending up at node 2 from node 1 is 0.31, but versus from node 3 is 0.13. But if you do it 20 times out, you see that these numbers are all the same. Your probability of ending up at node 2 is 0.4. Your probability of ending up at node 3 is 0.1. And that stability allows us to just extract their probability of getting a coupon, and we can use that in the key RDS estimators. This is true in general, and it's true even in like sparse, pretty clustered networks. Those things just take longer to reach that kind of convergence in this model. So Guile and Hancock have a nice example of this pretty sparse, pretty clustered little network right here. And what you see is if you graph the adjacency matrix and then turn it into a Markov transition matrix, you see there's a block up here and a block up here, and kind of limited connections between those 2 blocks. But even in that network, in a few steps, there's still pretty like high kind of separation between them. But once you start getting out to 14 steps, there are still differences within the groups, but it's getting better, right? And they're kind of becoming more and more consistent. So that probability, whether you have a 1/3 probability of being reached versus a 2/3 probability of being reached, is pretty much entirely dependent on your in degree. And we can explicitly solve for that probability. So in this network, this person has an in degree of 2, they're kind of a yellow color. This person has an in degree of 3, kind of an orange color. This is a 1 right here, light yellow color. And you can see that like the correlation between your in degree versus the kind of probability of being reached, regardless of where it starts from, is pretty strong. That feeds into a lot of the key kind of underlying assumptions of the weighting procedures of RDS. So RDS really does start with, as with any kind of method, there are a ton of assumptions for it to be valid. The kind of base assumption is that there has to be a social network. It has to be one social network. Everyone in the population is linked to that network. These are pretty unverifiable, and the way it's typically treated is this idea that we can assume that like anybody who's not in the giant component maybe is a small group or something like that. And then we typically have other assumptions like the community structure and homophily are weak because those allow us to get through that kind of blocky network that was shown previously much more quickly. So in the kind of typical RDS sample size, we might be able to create generalizable inferences. And then there's a number of assumptions about sampling. Traditionally, it was that sampling was conducted with replacement, that people only had 1 coupon, you started from 1 seed. These are kind of the traditional assumptions, and then various different newer RDS estimators have sort of selectively relaxed them to be able to account for branching structure, or multiple seeds, or maybe that the population size is not substantially larger than the sample size. So there are a lot of different kind of estimators used in the RDS literature, but almost all of them make assumptions about the recruitment process, or all of them make assumptions about the recruitment process and underlying network. And almost all of them really focus on respondent degree as the key metric that derives the probability by which you are likely to be sampled, right? So almost all of them are attempting to account for your probability of being sampled. The most classic one here is that your probability of being sampled is weighted average of your degree over the kind of total degree in the population. And that typically works pretty well. Like this is from another Giovanna and Jim paper where they simulated kind of an underlying social network, and then they, on that network, simulated millions of respondent-driven samples. And you can simulate the network with high kind of connectivity geographically or low connectivity geographically. But when you simulate the network, you see that the kind of degree of respondents versus the proportion of times that they get sampled is pretty strongly correlated. I think this is 0.96, 0.98. So it is a good approximation for that kind of probability, even under kind of different RDS kind of mechanisms or different violations of that, 2 coupons, 1 coupon, kind of those classic assumptions. The typical way degree is collected is that you would ask people, standard network name generator questions. How many people do you know that you know their name, they know yours, that you could, that are members of this population? Often people put restrictions on tie type. There's a lot of kind of measurement details that go into like how are you going to collect the degree data to make it the most relevant for the population of interest. And I want to emphasize that the classic kind of RDS literature tries to get people to recruit at random among their friends. That all those probabilities that I showed earlier, that idea that probabilities are converging as the sample gets further into the network, are premised on the idea that if I have 3 friends, I have an equal likelihood of giving it to friend A, friend B, or friend C, right? And to the extent that that's not true, that might severely bias kind of the estimates that are obtained from RDS. So typically we would give, you give people a kind of script when you give them a number of coupons, like here are 3 coupons for you to use to recruit others into the study who say are jazz musicians, right? Please make sure that the people you give coupons to are actually jazz musicians living in New Orleans or whatever. And they have not received a coupon from anybody else. When deciding who to give coupons to, don't give them to strangers. We want you to give them to friends. And if possible, try to give the coupons to different types of people you know. So this is not exactly the same as the random idea, but they're trying to enforce that in kind of a behavioral kind of sense. Just to reemphasize the random recruitment idea, this is conditional at random on who you have as friends. Your probability of recruiting others is going to be if you have 3 friends, it's going to be 1/3 to each of them, right? This doesn't mean that if you're a circle, your probability of recruiting a circle is going to be equivalent to your probability of recruiting a square, right? You have a 2/3 probability of recruiting circles and a 1/3 probability of recruiting square because 2 of your 3 friends are circles. But those probabilities wouldn't differ from the kind of conditional kind of structure of your local social network. Unfortunately, there's often the case that there's this preferential recruitment where circles are intentionally more likely to recruit other circles. Maybe they trust them more, maybe they think that they need to be in the survey more, that sort of thing, and that can add to substantial biases for the results. I just want to highlight that the main reasons for this typically are that people sort of have better relationships, that they want to help a friend who they think needs the money. This is a major kind of issue when designing RDS studies. If you set your incentive structure too high, you might end up in a situation where people are recruiting others to get the coupons, and maybe they make a side deal, like, oh, I'll refer you, and if you give me $10 of the $30 that I get for referring people, or something like that, or that you get for participating. So there's all sorts of ways that can lead to biases if incentives are too high. Also, sometimes people try and recruit others because they think that they need to get tested or something like that, which obviously would severely bias the kind of results you'd have. Just to highlight, there's a lot of different ways of thinking about this. I've tried to kind of, in prior stuff, think about a framework for thinking about this. What we find is that you end up with larger biases when people are preferentially recruiting on the basis of the attributes of who they're giving coupons to. Not as big of a bias when people are preferentially or differentially recruiting based on their own attributes. I'm going to skip that for time. So in designing RDS surveys, there's a lot of efforts in the last 10 years or so to include questions into the survey to test whether there are these biases arising. So you might ask respondents who participate in the survey, when they come back for that secondary interview, why did you give the coupon to the people you gave it to? And they might say, oh, because I trust them more. Or they might say, oh, because I think they needed the money. And if that's the case, that sort of is a flag that there's maybe something wrong with your recruitment, and you might want to adjust that. Another issue in RDS that I talked a little bit about last year, but I hadn't talked about in prior years, is this idea of kind of network evolution. This has been largely glossed over, I think, in the literature. But as Jim pointed out, networks change. You take a set of edges one day, that might be a very different set of edges among the same people a month from now or 2 months from now, right? And RDS studies typically unfold over a medium length of time. Some studies are pretty quick, that 12, 14 weeks, 13 weeks. But other studies, for instance, in Vancouver, where they had a sample size of 775, it took 36 months, almost 3 years, to recruit the sample. And clearly, when you think of, gay, bisexual, and other MSM, in Vancouver in, whatever year that was, 36 months, I bet that the kind of network connections among people changed. RDS studies haven't really thought about that. They're just measuring networks kind of at the time of initial kind of recruitment, and what they're generalizing to isn't certain. So we've done some work, it's kind of in review at stats journals, which take a fair bit of time, trying to estimate how much bias could arise from this. We do find that it can be pretty substantial if the network is churning pretty quickly and you're not using kind of newer, updated kind of degree estimates. So it can be useful, for instance, to collect degree a few times, both at the primary and secondary interview, et cetera. I mentioned that you can build in diagnostics. I just want to highlight there's a really nice paper called RDS Diagnostics that if you think about doing an RDS study, you should definitely read. It both provides types of things you should include in the survey, as well as some standard software that you can use to assess biases that might arise as the sample unfolds. One thing that I've highlighted in years past is that RDS tends to gravitate towards the center of the network, right? The most likely person to sample is the most central person, right? In a kind of degree-based kind of framework, degree centrality is pretty strongly correlated with many of the other measures of centrality. So RDS, even if you start, for instance, up here, you're more likely to end up sampling down in here. The black nodes here are the ones that I sampled in a simulated RDS on this network. There's also this kind of issue of bottlenecks in RDS. If we look at a network like Jim showed of a high school where there's sort of substantial racial segregation and friendship, you can see that this would maybe be a problem if you're trying to estimate the average race in that kind of high school. When you sample RDS on networks that have those kind of bottlenecks, they tend to, the results tend to be extremely variable, hundreds of times more variable than traditional sampling methods, which I'm going to come to as a very large problem for inferential kind of efforts. One thing that I want to preface as I move towards the kind of second half of the talk is this idea of bias versus sampling variance. So traditionally, most of the statistical work in RDS early on was focused on, can we use it to produce unbiased estimates of the population? Unbiased in this sense means the top two examples, right? Where all the things are very close to the target and centered, if you take the center of your, archery shots here, you get something that's very close to the bullseye. That's true in both the top left and the top right figure, right? The top right figure is less precise, but it's still, right on target. So almost all of RDS was trying to focus on that kind of minimizing bias kind of idea. The problem for RDS is that it does a pretty good job of getting you into that top framework, but rather than still all of the shots being on the target, they're spread super widely. And so you could imagine scenarios where RDS, for instance, produces on average unbiased results, but if you were to just do one RDS sample in a population, you might end up with an estimate that's really far from the population mean. And so I've tried to show this with a simple graph of precision and bias. So this is, imagine you did 1 million samples on the population, and sometimes you get a mean of negative 4.5, and sometimes you get a mean of positive 4.5, and this is the distribution of mean, like a histogram of the means that you get across that population. There's a substantial spread in that. Whereas in this sample, or in this method, which is a little bit biased, if you were to do a lot of samples, almost all of them are pretty close to the mean, but the average here is like biased. It's not where the mean of the population is. Whereas the average of the red line is right here, but it's very, very imprecise. And that's sort of the key problem for RDS, is that it produces unbiased estimates typically, but it is highly variable. So you might do one sample. Imagine you had infinite resources and you did 2 RDS samples of the same population, day 1 and day 2, right? And day 1, the mean might be 10%, and day 2, the mean estimate might be 90%. That is a huge problem for making any kinds of inference. So typically, when we're thinking about this, we want to think about both bias and precision in sort of sampling approaches. In traditional sampling, what happens is as you increase sample size, you end up being closer, like this red line, while the center of mass stays at the correct parameter, the red line just becomes more pulled in close to here. And so each individual sample is less likely to be far. That's the traditional law of large numbers kind of sampling approach. But for RDS, that doesn't actually hold, which took a while for people to discover. So contrasting RDS with simple random sampling, if you were to sample 1 million kind of RDS samples in a particular population, I just use this one here, and we're trying to estimate the proportion that is kind of racial minority, which is clustered in this kind of community. If we just sample 150 cases, we see that what you end up with is with 500 samples with 150 cases each, this is sort of the distribution of RDS samples. You can see that it's pretty much unbiased, but it's pretty wide. Whereas with 500 cases with simple random sampling, we end up with a much less wide distribution that is also, if I graph the bins a little bit differently, also unbiased, right? And that's a nice feature of simple random sampling, but RDS doesn't seem to have that. So when we increase sample size even more, it doesn't improve that scenario dramatically. One caution I want to give here is analytic estimates of RDS kind of empirical kind of results where they took, for instance, the National HIV Behavioral Surveillance System did RDS in Seattle in 2009 and 2011. When they took the estimates for Seattle versus Georgia or versus Atlanta versus Miami, when they took those and did like a test-retest correlation, the variability is not as large as the kind of mathematical and simulation-based models would imply. So there maybe is something that's happening in the actual unfolding of these samples in reality that kind of obviates the problem of high sampling variance, but people have not diagnosed what it is that is actually creating that likely good thing. So RDS in that large statistical apparatus has a lot of different estimators to try and come up with how we can understand the population mean and also how we can kind of quantify the uncertainty of that population mean. So there's a bunch of different ones. They take, almost all of them take the degree of the respondent into account, but they often include slightly different things. Some of them, for instance, try to adjust for the fact that RDS is not a with replacement sampling process, it's a without replacement sampling process. So they adjust for that. Others try and take into account other information that might be collected. So one that I really like is this linked ego networks estimator, where he asked people in an RDS, well, what proportion of the people that you know share this attribute? And in addition to their own kind of status, that feeds into the estimate itself. So not only am I getting information like, oh, I am an unhoused person who plays jazz in New Orleans, but also I know X number of other unhoused people. So with that network reporting, he can build that into the estimator and come up with a slightly more, substantially more accurate estimate. Of course, that doesn't work for things like HIV status, which you can't really expect that individuals would know other people's HIV status or their condom use or things like that. And there's also a lot of efforts in kind of the last 5 to 10 years in RDS to estimate things that go beyond prevalence. One of the estimators that I think is really promising is this, what Guile and Hancock called the model-assisted mean estimator. So in that, they take the RDS data, they fit an exponential random graph model to the data, and then they predict what the network would look like. The reason they predict what the network would look like is then they can simulate a bunch of RDSs on the network and come up with a new estimate of the mean, a new estimate of the sampling variability, et cetera. But what hasn't been done as much is using that predicted network and the features of that to try and understand cool network things about the population. So I think that's sort of an underexplored area of using the RDS data to learn about social networks more generally, and potentially with the ego network estimator I just mentioned, or the kind of aggregate relational data that is sometimes collected to understand population sizes or group interactions. I think there's a lot of ways that you could use RDS data to learn more about social networks more generally. One that I've tried to do is estimating the clustering coefficient from different networks. So what's the probability that your friends are friends with each other, right? That's the kind of classic notion of clustering in networks. And if you estimate the clustering in networks with RDS, you can use a couple different methods. One is you can ask people like, what percent of the people that you could recruit does your recruiter know, or does your recruiter know the people that you did recruit, and use those to feed into estimates of kind of the clustering coefficient of the network, which in a separate paper I showed is actually pretty strongly predictive of kind of diffusion dynamics, at least for HIV prevalence in kind of co-injection networks. So co-injection networks, these are 2 cities in the Philippines. One is Cebu, one is Mandawi. They're about 10-minute drive from each other, and there's a lot of things that are different about them, but a lot of things that are sort of similar about them. What I found is that they both had very low levels of HIV prevalence in their people who inject drugs networks in 2011, but in 2013, one of them had a big outbreak where it moved to 35% HIV positive, whereas the other, no real change, right? It stayed at about 3.5%. The degree distribution in these two networks was almost identical. The one thing that was substantially different, this is the clustering coefficient, 35%. That HIV moved from about 5% to 50% and stayed at about 5% in the other city. The clustering coefficient in the city where HIV exploded was substantially higher, suggesting that maybe this drives some of the diffusion dynamics in ways that Jim has thought about a lot, with clustering being a boost for diffusion dynamics. So early RDS work really did focus on that bias kind of issue, but sampling variance, I've tried to say, is absolutely critical. You only get one sample in reality, and the fact that if you did 1 million samples, you'd have an unbiased estimate is not particularly useful if each individual sample has a pretty high probability of being very far from the population mean of interest. Another related concern to that is, can we even detect that we're in a situation that has high variability? So early work by Matt Salganik and others first started to diagnose this, showing that when you run lots of samples of RDS on particular networks, that the variability that you get from those results is really, really high, substantially higher than traditionally assumed. It used to kind of, I think, just off the top of people's head, they were like, oh, RDS, you need twice the sample size to make the same level of statistical power as traditional sampling methods. But this work showed that you need 5 to 10 times the sampling size to get the same statistical precision as traditional sampling methods. So this is a big potential problem. And worse, kind of some of the stuff that I worked on suggested that not only is that the case that you need substantially larger sample sizes, but your confidence intervals will be super biased. And they will actually tell you that you don't need substantially larger sample sizes. And that's a big problem for RDS. I'll give an example of why that would be a problem. So imagine we have people who inject drugs in 2 cities, and you're interested in looking at hepatitis C prevalence. So these are totally made up numbers, but imagine city A has 55% hepatitis A, hep C prevalence, city B has 25% hep C prevalence. RDS variance is so high that the method can sometimes be almost worthless. So you might say from the one sample that you ran, or if you were to run 1 million samples in these surveys, in these studies, maybe the average is 40% in one and 50% in the other, right? But the range of estimates that you should be getting is 5 to 85%, right? That should be the range of estimates if you were to run a bunch of RDS samples. But unfortunately, you just run one RDS sample and you calculate the sampling, the confidence intervals that you might want to use. The confidence intervals might tell you that, oh, it's 35 to 45%, rather than like RDS only has the ability to detect something between a 10 and 90% kind of range. And so that was a classic problem that RDS faced that has been a very big challenge. I think of this as like the unknown unknown, right? That you have a sampling method that tells you we have a relatively small band of kind of possible estimates that are consistent with the sample that we got. And in reality, that band should be much larger. So you're saying that city A has lower HIV or hep C prevalence than city B, but that is completely inaccurate. Your method has no validity to tell you that, right? So that's a big challenge. Thankfully, newer kind of variance estimators that have been implemented in kind of newer R packages do solve that. So if you're doing RDS, I really encourage you to use the kind of latest software in R to be able to estimate like the tree bootstrap variance, because the 95% coverage interval should be 95%, but several of the existing estimators were only saying certainty levels. They were saying substantially less uncertainty than there is. So you really, if you're doing RDS, use the new kind of software for it. I have a few notes on web-based RDS because I got asked this like every time I've presented. Web-based RDS is a real challenge, and there's a lot of kind of open areas to develop a stronger set of protocols. I think the biggest challenge for web-based RDS is verifying that the people are not participating multiple times, that I recruit Lynn into the survey and she participates, and then I give her some coupons, and then she logs back in and says, okay, I'm redeeming this coupon, and then logs back in and redeeming this coupon. Like, you could have a real problem in your samples if that's the case. I think the real promising direction is obviously Zoom-based interviews for that, but people have not kind of formalized protocols for that. So I think that's an open area that's kind of exciting. RDS also typically has problems when you're fielding it, so it's not uncommon that people will start an RDS sample and realize, oh, I need to give more coupons out, or I need to enroll new seeds. So there's some suggestions here for ways to think about this. So the benefits of RDS is that you can weight the data and kind of create inferences. The big challenge is that it is a highly variable sampling method. Any particular sample you field, the mean estimate that you get from that sample might be far from the true mean in the population. But I think it's exciting, it's fast, it's relatively cheap and effective, and you can learn a little bit about networks from it. However, I think that there are other ways we can think about collecting this kind of data that might push us even further forward. So one that I proposed, and Giovanna has done a lot of work kind of pioneering the actual, I proposed with Ted Mao. Giovanna has done a lot of work with Ted Mao in pioneering how to do this in practice, not just on a computer simulation or in math, is this idea called network sampling with memory. So RDS suffers from that high sampling variability, particularly when there are kind of structures in the network. So this approach was really trying to say, okay, well, we can't see if there are structures in the network, but how can we learn about the network as the sample goes on and use what we've learned to change how we're doing the sample in an adaptive way to more effectively get cases into the survey and to get estimates that are usable. So we've tried to modify data collection, not the estimation procedures behind RDS. The example that I always give of this is this network where there's two clusters, right? Cluster X and cluster Y, and only one link between the two clusters. If we start sampling in cluster X, we have a low likelihood of transitioning into cluster Y. But what we do in network sampling with memory is we collect data on how many times, we collect data on people's reported alters, and not like, oh, I know Dana and I know Craig, and not like identifiable data, but minimally identifiable data. I know somebody whose name starts with D and last name starts with P, and they work at Duke, right? So like very minimal identifying information. And when we collect that for everyone in the network, we can start to see, oh, Ashton could have nominated Dana, Jim could have nominated Dana, et cetera. And when we use that kind of information about how many times somebody was likely to be nominated, we can then adjust the probability of recruiting the next case. And so what we do here is we say that when we get to node 7, we see that node 1, which is a square, has only been nominated one time when node 7 is reached in the sample, whereas all the circled nodes have been nominated more than one time by somebody who's in the sample. So the basic idea, at its simplest version, is just to push people to recruit those who have only been nominated once versus those who have been nominated multiple times. And by doing that, we cross over the cluster, and then we can sample within the other cluster pretty effectively. And even that simple procedure works really well. So we collect minimally identifying data from the respondents, minimally identifying data about the nominated but unsampled nodes, and we keep a list of who those people are. Not identifiable information about them, but like what we think is the exhaustive list of that group. And we estimate the network size at each step, and eventually by doing this, the theory is that you can recover the network sampling frame, like who is in the population, and from that draw with replacement simple random sample. So we have different modes for the method, and the idea is to try and get there as fast as possible. So the first mode is we call search mode, where we try and explore the network, and the second mode is called list mode, where we try and most effectively sample the network to get generalizable kind of inferences from it. So it's kind of a blended adaptive sampling design. The idea here is that as you move through the network, you can come up with an estimated size of the network using a capture-recapture method, like number of people on the list who are nominated one time over the number of people on the list overall, or vice versa. And you can look at the number of nominated nodes you have. And those two properties converge, and we think that that offers a good stopping rule for when you kind of can end sampling and feel pretty confident about your results. So we tested this a lot of times in empirical data and analytical data, and we found that it works extremely well, even in super clustered networks. So this is one ad health network, very, very clustered by race ties, one race group substantially smaller than the other race group, differences in degree across the groups, et cetera. And what we find is that when we simulate RDS in this method, in this network, we have huge variability in the estimates of proportion black, for instance, which makes sense. But when we simulate the network sampling with memory approach on this, the proportion black estimates converge to the correct result and have very, very low sampling variability, or the ratio of sort of the sample size you need for a network sampling with memory versus the sample size you need for a simple random sample to be able to have the same kind of precision in your inferences, approaches 1. So it's almost as effective as simple random sampling. So it's a really, really easy way to kind of explore the network and come up with viable estimates about the properties of that network. This is sort of the classic NSM approach. As the sample size increases, we see our kind of confidence intervals decrease, and we end up pretty close to the population mean, which is very similar to what you would see with a simple random sample, right? The additional, after you get to 500 cases, the additional gains of sampling other people maybe are minimal. That very first graph I showed of the kind of estimate declining over time. Whereas with RDS, that process is not true at all. RDS, if you simulate 1 million RDSs or 1,000 or 1 million RDSs on this, the top 5% of estimates stay pretty high, the bottom 5% of estimates stay pretty low, and although it's unbiased, like these blue lines are approximately the same place, you don't get benefits from sampling additional cases, which obviously is a huge problem if you're trying to make statistical inference, because that means that you're saying things like, in this school, it's something between 1 and 99% black, which is not a useful estimate, right? It might as well not have done the survey. We've tried this a bunch of different ways. Here, this refers to the classic way we proposed, and then we tried other ways of thinking about only collecting data on 3 ties, or 15 ties, and only collecting referral information for 3 of them versus 2 referrals, et cetera. The basic properties are all the same when we tweak the actual in-practice kind of sampling procedures. Obviously, the best would be collect all the data about all the things that you can. So you say, tell me about all of your friends and give me contact information so that we can make referrals for all of them. That works really well, but these work pretty well as well. Similarly, we tested different things of like, how do you make the decision to switch from that search mode to the list mode? And there are differences between these that kind of matter in practice, but the general result is that NSM works extremely well. So that's what Ted and I had done on this kind of mathematical aspects of this, but then Giovanna kind of came in, and with her expertise in survey data collection and the practicalities of methods rather than just messing around on computers, she was able to solve a lot of the implementation challenges that we hadn't really anticipated, and designed a really great survey funded with an R21 for Chinese immigrants in the Raleigh, North Carolina area. Data with Dupree, I think, seed funding to survey Chinese immigrants in Tanzania using NSM, and through those procedures, as well as others like a sample in Paris, a sample in Ghana, et cetera, she came up with a lot of kind of protocols and manuals that are beginning to be published and things like that to make network sampling with memory a more feasible method for other people to implement. And one of the things that I wanted to come back to in Giovanna's kind of work, in the Chinese in Raleigh-Durham area, she chose Chinese because they're well represented in the American Community Survey, so they're sort of a gold standard population we can compare the estimates against. And what was really cool with the NSM study that she fielded here is the estimates worked very well in comparison to the kind of ACS data collection on that population. So they were very similar in a lot of respects. She also did really exciting things like testing differences between in-person interviews, phone interviews, web-based interviews, all of which led to kind of interesting results. And one of the most exciting things to kind of bring it all back is the cost per interview of a really small sample was substantially lower than the cost per interview of classic samples like PSID. PSID, if you remember those numbers that I gave at the beginning, like 275, that's for the web mode of PSID, which they fielded to 10,000 or so people, right? To collect, and when you field something to a larger number of people, the cost per case goes down, right? But when you're looking at only, I think, a couple hundred people here, to achieve web mode costs of $84, like one-third the amount, really suggests that this is a very promising method for kind of sampling populations of interest and coming up with exciting ideas. One other cool thing with NSM is because we get all that data on the nominated but unsampled nodes, we can learn a little bit more about network structure. And last, you can design NSM to look at kind of multi-site things, which Giovanna is working on presently. So I think there's a lot of possibilities with it. Advanced protocols have a large amount of promise, but we have to combine a lot of these ideas to get kind of the best practices for collecting the data. There's a lot of data collection activities that need to be worked out. And my big critique of RDS for a long time has been a lot of attention has been paid to the statistical aspects of it and not to the research design aspects of it, of how to actually field the data. And that's where I think NSM is an exciting area to move forward. So thank you. Oh, yeah.
Hey, thanks a lot for that presentation. It was really interesting. Can you talk a little bit about the practicalities when you're collecting the data, and then you need to go from understanding who may have only been nominated once to getting that person to actually do the recruitment?
Yes, so the way that it's been done and implemented in the field, Giovanna could probably speak a little bit better, but typically we collect the contact information from the respondent, the initial respondent. So we say, who are you willing to give us the contact information, like a phone number or something for these people? And then there's been different ways that you've tried it. One has been that the researcher calls that person themselves. Another one is that you ask the person to refer somebody with phone number, that ends in 6423 or whatever. And so those different approaches have yielded kind of different levels of success.
Then we usually send also, once we recruit the respondent, we also share with the respondent an alert message that we ask the respondent for their nominated authors in order to encourage them to participate in the next way.
How much of a gap is there in time between getting their name and contact information, doing the calculation to figure out who would be appropriate next person?
In fact, sampling, this does not need to happen chronological at the same time, right? The sampling you see is once you have selected enough. You have enough referrals, so the sampling over the network, right? At the same time, once we have sampled responses in the first wave, say, then we share this message with the college network. And I can talk to you more about steps. There is no delay as long as the respondents are shared with referral information.
To follow up, maybe this is part of the ethics conversation, but how are you dealing with not revealing, potentially stigmatizing information of your author, and then the researcher is calling them saying, hi. How do you deal with that?
The IRBs for this have been extensive, and we try and do everything we can to maintain the confidentiality. So usually, we're doing a survey, and if you were referred into the survey, I think it's the typical way it's done, or having the person contact the other person to get them to that contact.
There's also a difference between RDS and NSM, of course.
Yes.
Because RDS, really relies on anonymity, so it relies on the respondents who do the recruitment, right? So there is less interference, of the researcher. Or NSM, there is more participation, by the researcher, and there is also some collection, right? So it really depends.
Yeah, so that really drives home this key idea that RDS works very well for highly stigmatized behaviors, things like that, and NSM would not work in some of those circumstances. And that's always going to be a trade-off that you're going to have to make. NSM might work better if you're interested in things like immigrant populations or other groups that maybe the threat of them, the deductive disclosure for them is lower than it is for other populations like male-sex men in Kenya or some countries where it's Uganda where it's illegal.
All right, one last question, and then we're sort of
I'm wondering if there's been any use of RDS applications
juxtaposed efforts to do that and to secondarily enroll all the people who participated in the RDS to then enroll in the clinic. So it was sort of a dual process. We had this intervention, how many of we use RDS to sample the population, how many of them in the sample enrolled in clinics, and anyone who didn't, can we give them the intervention as well to get them to enroll in testing?